Good morning, all of you. Welcome to another session on computer organization and architecture. This is Dr. Diana here. When we started with the design of a hardwired control circuit, we looked into the operation of the circuit and we started deriving the control information for different types of instruction. So, this is the circuit that we started coming up with. So this is our basic idea about our hardwired control unit with two decoders, and we are taking input from the instruction register and the external clock input. Based on the instruction register, we generate signals D0 to D7. Based on the clock, we generate timing signals T0 to T15. So this we have already seen, and we have also seen that time cycle T0, T2 and T0, T1 and T2 are same for all types of instructions. So in the first thing, we actually take the program counters PC's value into the address register. From the address register, we look up into the memory, read it into the instruction register, and increment the value of PC by 1. And then we saw at time cycle T1, we have received our input at instruction register. At time cycle T2, we decode that information and send bit 15 into flip-flop I, bits 0 to 11 into address register, and bits 12 to 14 into the decoding circuit. This decoding circuit generates signals D0 to D7. And we also saw that D7 can be 1 only for register reference and IO kind of instruction, and its value is 0 for memory reference instructions. So based on the value of D7, we can distinguish between these instruction types. And then we look into the value of flip-flop I to see if it is a register reference instruction or an IO operation. When D7 is 1, either of this is possible. When D7 is 0, if I value is 1, it is indirect memory access, and when D7 value is 0 and I value is also 0, it is a direct memory access instruction. So at time cycle T3, I can directly start executing my register reference or IO instruction. And in the case of memory reference instruction, I might have to refer to the memory twice for indirect access. So once I refer to the one memory reference, I complete at time cycle T3 for indirect access. For direct access, because that value is already available in the address register, I am not going to do anything. This nothing phase is used for synchronization between direct and indirect memory access instructions. So from time cycle T4 onwards, whether it is direct memory access or indirect memory access, I can use the address register itself for receiving the data. So this is what we have seen earlier. Now we will start with explaining our set of memory reference instructions. So when I say memory reference instruction, at D7 dash, at D7 dash, it can either be I or I dash. At time cycle T3, we start with our execution. So D7 dash, if its value is I, or if the value of I is 1, I mention it as I. And at time cycle T3, I bring the exact operand's address inside the address register. So now I have the data's address in the address register, be it direct or indirect. It's available now. And at D7 dash I dash T3, I do nothing. This is for synchronizing direct and indirect memory type of instructions. Then we understood I can have 7 different types of memory reference instructions because I've got 3 bits in the instruction register that indicate what operation can be done using the memory access. Any memory reference instruction will have the address in the bits 0 to 11. When address is available here, one of the operand is available in memory. This has to either be brought into the accumulator or inside the data register for further processing. So always address register and another register, data register or accumulator, will be used as gateway. So when every time I try to read from the memory, it is always through address register. And every time I read some data or write some data inside the memory, it is always through either the data register or the accumulator. That's the idea behind. And the bits 12 to 14 are used to distinguish between different memory reference instructions. So this is given as input to the decoder, and the decoder generates signals D0 to D7. And D7 cannot be 1 for any of the memory reference instruction. So that's according to our instruction format. So I can have values of D0 to D6 set to 1. So based on the values of D0 to D6, if D0 is 1, D1 to D6 will be 0. If D1 is 1, D0 and D2 to D6 will be 0. That's how the decoder's output functions. So one of these values only can be high at any point of time, and depending on which bit is high, I can execute one instruction. So I've got 7 different instructions under the memory reference category with values D0 to D6 set to 1 for each of these instructions. So that is my idea behind. Now I look into the set of instructions. The first instruction starts with D0's value set to 1. And the instruction is an AND instruction. When I say AND instruction, I am performing an AND operation between 2 binary values or 2 data values. One of the data value is given in the instruction itself in the address register, and the other data value by default is the accumulator. So I am going to perform an AND operation between accumulator content and some data which is held in the memory. Because I already said I cannot directly operate on a data which is held in memory, I should bring it either to the data register or to the accumulator for any process. Because I am working along with the accumulator in the AND instruction, I cannot bring it to the accumulator. I have to bring it into some other register. For now, I will take into data register. So the first thing I perform is I should bring memory content into, I should bring that memory content into the data register. So at D0 at time cycle T4, I am going to bring something into the data register. The data is brought from the memory location addressed by the address register. So I bring the content of memory into the data register. Available? Only after it is available at the data register, I can perform some operation on the data register. So at time cycle T5, I have to perform the AND operation. Okay, the AND operation is indicated using an upper cap symbol. So upper cap symbol, accumulator is now, we do an AND operation with the accumulator, upper cap symbol with the data register content, and the result is always stored back in the accumulator. Accumulator is called the scribbling pad of the computer. So any temporary results that you have, it will keep overwriting on the accumulator. So now we have got the result in the accumulator. Once I complete this, my execution, the instruction execution is complete. Once the instruction execution is complete, I should clear the sequence counter to 0 to indicate that the computer can start with the execution of the next instruction. So I am going to set my sequence counter to 0. Clear? Now these are the 2 operations to be performed. Done. This is when D naught is 1. This is the first instruction under the memory reference category. The second instruction under memory reference category is when D1 equal to 1. When D1 is equal to 1, the operation that is performed is a add operation. The operation is add. Add means I have to have two data values. I am going to add both of them. One of the data value will be there in the accumulator. The other data value will be read from the memory. So it is going to be very similar to this, but instead of AND operation, I am going to perform add operation. That's it. So add, I cannot have the value D0, I should have the value D1. D1 is 1 and D1 is 1 and at time cycle T4, I read the memory content of address register into the data register, ready. Then when D1 is 1 and time cycle T5, I perform the add operation between the accumulator and the data register and store the result into accumulator, and then I clear off the sequence counter. So the sequence counter is now cleared. So it indicates that this execution is complete. The next instruction is at D2 equal to 1. So the instruction when D2 is equal to 1 is called as load accumulator. Load accumulator means LDA. This is a simple read operation when I try to read whatever content is there in memory into the accumulator. So this is a very simple read operation. So I have to mention D2 at time cycle T4. I can directly read inside the I should bring the content into accumulator. So I am going to use the data register because data register is the gate register. It's like every time you cross in and out of memory, it should go through the address and the data registers. So at time cycle T4, I should first bring the data from the memory location addressed by address register into the data register, and at time cycle T5, I bring that into the accumulator from the data register, and then following that I clear off the sequence counter. So this is called as load accumulator. So this is how I load the accumulator with any data to be read from memory. Okay. Now this is done. Till D2 is equal to 1, we have completed. The next instruction we will see is when D3 is 1. What happens when D3 is 1? Now the next instruction is when D3 is equal to 1. D3 equal to 1 indicates a store operation. So store operation is symbolically represented as STA. Now STA means I should store some content which is in accumulator into the memory addressed by the address register AR. So whatever is the content of accumulator, I am going to put inside the memory. That is called as the store operation. So this can be done as D3 at time cycle T4, then at time cycle T4, I have to send into memory. So the destination is memory location addressed by the address register, and I am sending the content of accumulator into memory. So the content of accumulator is sent to memory. This is done completed in one clock cycle itself. So immediately I can clear off the sequence counter. Clear. This is store accumulator. Now D4 equal to 1. The next instruction has D4 equal to 1. When D4 is 1, it is called as bun or branch unconditionally. Branch unconditionally. Now we should understand what branching is before we try and explain this instruction. Branching is done when I try to alter the normal flow of execution. How does a program normally execute? Imagine this is my memory, and at memory location 100 I have some instruction. And I have a subroutine which starts at 150. We all know what subroutines are, right? It's a subprogram. Just like C program, know how we have functions. We call them as subroutines in assembly language programming. The programming that we do here is assembly language programming. Okay, I have a subroutine at memory location 150. In the usual flow or in the usual organization, program execution, my program counter holds the address of the next instruction to be executed. Assume I have the instruction load accumulator with some memory address value 130. This is my instruction that I am executing, and I can have it as indirect memory access. So this is my instruction. When I am executing this instruction, the program counter's value will be 101 because the program counter points to the address of the instruction to be executed next. Okay, so the next instruction that I want to execute is at memory location 101, which is the next memory location. This is the normal flow of execution. Now imagine I have a subroutine at memory location 150. Okay, at memory location 150, if I have a subroutine, I have to execute that immediately after this LDA operation. Okay, if that is the case, I can transfer, I have to indicate the control system that instead of executing the instruction at 101, I have to start executing some instruction at this location. Every time a subroutine is starting, the first location of the subroutine is left as empty and it will start its code from the next location. So this is part of the subroutine only. But the instructions will start from 151. So this is how it is. So now I have to start following a different execution path to find, say for example, I have a if operation. I check some value, and if the condition has been satisfied, I have to exit the program. So I place the exit at one particular location. Whatever conditions I check there, I should go to this place. So I should exit from the program. So that's my intention. So I have placed the exit at location 150. I should tell the computer that instead of executing the instruction at 101, which it is expecting, the program counter is expecting to execute the instruction at 101. I have to tell it to go to location 150. Where is this 150, I have to place this 150 somewhere. Okay. So the branch unconditional, if I use it here, imagine I have 150. So after load accumulator, I started executing the branch unconditional instruction. When I am executing branch unconditional execution, the current instruction is 101. So the program counter value will be 102. It is expecting to execute the instruction at 102. Instead, I have mentioned that it should branch unconditionally to memory location 150. So, what should I execute next? The instruction at 120. How does the computer understand which is my next instruction or the location of the next instruction? Through the program counter. So, I am going to update the value of program counter to the instruction I want to execute next. So, I am branching unconditionally to the location 150. So, 150 becomes the location of the instruction I want to execute now. So, in that case, what happens is I have 150. My program counter value is taken. My program counter value has to be updated from the content of the address register. So, the address register content is directly put inside the program counter to indicate which instruction I am going to execute next. So, when I am doing this at D4 and at time cycle T4, I am going to update the value of the program counter with the content of the address register. Is that clear? So, this is called as branch unconditional. So, I have branched unconditionally to a location to the PC value is updated to 150. When the PC value is updated to 150, the computer understands that the next instruction to be executed is found in 150 and it throws the execution to this particular location. Or it starts reading this into the instruction register next. Is that clear? So when this is complete, I can clear off my sequence counter. Okay. So this instruction is called as branch unconditional. So we have looked into instructions starting from D0 equal to 1 to D0 equal to D0 1, D1 1, D2 1 and D4 1. So when I try listing these instructions, the next instruction that I have to execute is when D5 equal to 1. So I have to see when D5 equal to 1. This place is easier to focus. So I'm just reusing the same space instead of writing to the other column. If I write here, I think it will be easier for you to see in the video. Okay, now the next instruction that I execute will be when D5 equal to 1. D5 equal to 1 indicates an instruction called BSA. Branch and save return address. Branch and save return address. and D6 equal to 1 indicates an instruction called ISZ, which is increment and skip if 0. These are the other two instructions under the memory reference category. We will be looking into these two instructions in the next session. And for now, I'll just do a recap of the instructions which are required under the memory reference category. So whatever we have done earlier, I'll just redo it once again. Okay, so this is done. Memory reference instructions are executed when the D7 value is 1. Only when D7 value is 0, it indicates a memory reference instruction. Okay, so all memory reference instructions start from D7 dash or when D7's value is 0. The value of I can either be 1 or 0, indicated as I or I dash, and they start execution at time cycle T3. So, if it is a direct memory access, I can fetch the address directly from the memory location addressed by the address register. But if it's indirect access, I have to redo that reference process once again to get the actual data. So a double reference is required for a indirect memory access. So if it is indirect memory access, the value is indicated with I equal to 1. So D7 dash IT3 indicates an indirect memory access. When that is the case, I do the reference of memory once using the address register. I am bringing the memory content of address register inside the address register. This is for completing one of the memory reference. So this is when this is done at T3, if it is direct memory access indicated with I value 0 or I dash, then I do nothing. This process is done so that I can synchronize between indirect and direct memory access instructions. So when that is done, I have completed synchronization between indirect and direct memory access instruction. So that at time cycle T4 onwards, the address of the data to be used for execution is available in the address register. I have completed either one reference or two reference based on my requirement, and I have brought that address inside the address register somehow by the end of time cycle T3. And then we moved on into time cycle T4. At time cycle T4, we have to identify what is the exact instruction we are executing, and that can be derived from the bits 12 to 14 of the instruction register. So that I have given as input to the decoding circuit, and signals D0 to D7 are generated by the decoding circuit. D7 is always 0 for memory reference instructions, so I cannot look into D7. The other combinations D0 to D6 can be used for further processing, and then I look into that to see what is the exact instruction to be executed. If D0's value is 1, then I execute an AND instruction. If D1 is 1, then it is a add instruction. So I add the content of the accumulator and whatever I find in memory, I add them together, put the result back inside the accumulator. And D21 indicates a load accumulator operation. So I read the memory, bring that content inside the accumulator in load accumulator instruction. And when D3 is 1, we perform a store accumulator operation, or the content of accumulator is stored back inside memory addressed by the address register. And when D4 equal to 1, we perform the branch unconditional operation, where the address of the next instruction to be executed is up, which is available in PC, is updated with the content of the address register. So whatever I specify in the address register, or whatever I specify in 0 to 11 bits of the instruction register, which is now available in the address register, can be used to update the value of the program counter to indicate the next instruction to be executed. This is called as branch unconditional operation. In the next session, we will look into branch and save return address and skip, increment and skip if 0 operations. These two are instructions, memory reference instructions, when they are performed when the value of D5 equal to 1 and D6 equal to 1. With this, I will stop for today's session. Thank you one and all. Stay home, stay safe. Looking forward to seeing you all very soon. Thank you.